Hi guys, welcome back. So today what I wanted to go over was this concept of horizontal saccadic movement. So saccadic movement refers to basically the movement of your eyes where you shift your fovea rapidly from one point of interest to another. So if you remember, the fovea is the part of the eye that actually kind of detects most of the light, gives us most of our visual acuity. So it's basically what allows us to shift our focus rapidly between two kind of interesting points. So if you held two fingers out in front of you, two fingertips, one on each hand, then the saccadic movement is you switching your field of view from one fingertip to the other. So that's what we're going to try and go over today. And basically we're going to discuss how we coordinate it so that when one eye moves, the other eye also moves in the same kind of direction so that we can keep our vision kind of constant so that we don't get double vision. So this kind of diagram that I've put up here to start off with is quite complex. So don't stress too much. There's a lot of information here, but this is kind of going to illustrate some of the key areas we're going to talk about. Most of the things that we're going to be talking about today are going to be located in the pons, in the brainstem. We're going to cover things such as the paramedian Pontine Reticular Formation, or the PPRF. We'll also discuss a little bit about the MLF, the medial longitudinal fasciculus, and we're going to discuss a little bit about the different nuclei for the cranial nerves involved in eye movement. So before we go into that, it's first important that we understand the different types of extraocular muscles. So these are the muscles which attach to the globe, which is the eyeball, and they are what allow the eye to actually move around in the orbit. So there's a few key ones that we should know about, and these are listed here. Well, I guess these are the only ones that we have. So superior oblique, inferior oblique, superior rectus, medial rectus, lateral rectus, and inferior rectus. For these guys here, the recti muscles, their name pretty much gives away what they do. So superior rectus, you can see, attaches on the superior aspect of the globe, and so you can tell that if this bit contracts and pulls back here, it's going to pull the eyeball up, right? So superior rectus pulls the eyeball up. Medial rectus is this one here. It's coming in and attaching on the opposite side, and close to the nose here. And that's gonna, when that contracts, it's gonna pull the eyeball kind of towards the nose. We call that adduction. So adduction. So that's twisting the eyeball back in towards the nose. The lateral rectus is responsible for the opposite movement, abduction. So moving your eyeball out away from the midline. And inferior rectus is involved in pulling the eyeball back down. The harder ones, I guess, are trying to get your head around a superior and inferior oblique. These muscles attach in a bit of a weird way so that they actually do the opposite movement, I guess, to what their name suggests. Superior oblique, you can see, kind of hooks around this pulley system here and attaches in such a way that when it contracts, it doesn't pull the eyeball up, it actually spins the eyeball down in a way. So what this is involved in is if you're looking, if your eyeball's point is adducted, so pointing towards your nose, and you want to look down, then superior oblique contracts and pulls your eye downwards when it's facing the nose, so when it's adducted. And inferior oblique kind of attaches in similar. It's got another pulley system so that when you're looking towards your nose, so when you're adducted, when it contracts, it's going to pull the eyeball up instead. So when you're adducted and looking up, that's your inferior oblique that's engaged there. Levator palpebrae superioris, we don't need to worry about that too much now. That's kind of in there for completeness. That's one of your eyelid muscles. So yeah, that's not necessarily an extraocular muscle. In terms of the nerves innervating these, the nerves involved are cranial nerve 3, cranial nerve 4, and cranial nerve 6. So 3 is oculomotor, which kind of makes sense. 4 is trochlear, and 6 is abducens. So the easy one to get out of the way first is abducens abducts, right? And so remember, the muscle that abducts is the lateral rectus. So this is cranial nerve 6. Done. The next one is trochlear. Now, trochlear is responsible for the superior oblique muscle. Cranial nerve 4. All the others are actually done by oculomotor. Cranial nerve 3. And even superior, levator pulpobase superioris is also cranial nerve 3. So, oculomotor is the biggest nerve out of all of these exiting the brainstem, because it controls so many of these muscles. And so, one of the things you actually see is if you have a cranial nerve 3 palsy, so this isn't working, you'll see what's called a down and out pattern, and that's because the ones that are going to be engaged is going to be your lateral rectus pulling your eye down, and your superior oblique is actually going to involve it having a downward kind of turn as well. Now, I know that we said that the superior oblique is mainly engaged when your eye is adducted. However, it does still have some kind of downwards pull when the eye is abducted as well, abducted. So if we lose cranial nerve 3, we have this down and out appearance. So if you've got someone's nose there, one eye here, the other eye is going to be pointing down like this. So that would be if this is right and this is left, that would be a right cranial nerve 3 palsy. Cool. That's not the focus of today's talk though. So today what we really want to be talking about is this concept of saccadic movement. So if we're going to be moving our eyes, so similar kind of thing. So if someone's looking at us here, oh, that's not a very equal eye. That's still not very equal, but it's a little bit better. That's their nose, right? So say that we're getting this person to follow my cursor, right? And if we get them to move, if I move the cursor over here, then we're going to be engaging the lateral rectus muscle here and the medial rectus muscle here, so that the person can follow the cursor over to this direction here, right? So we're actually engaging the opposite muscles in a way, the lateral rectus here, the medial rectus here. And that's quite a complex process. And they're engaged in the same way so that both eyes should move at the same time, and so that this is constantly kept in focus the whole time. So, if we keep going down now this is the pathway here that we're going to draw out. So I've got a key on the side here with the PPRF, so that's the Pontine Paramedian Reticular Formation I was talking about before. Now, this is kind of interesting. So this is what controls our horizontal saccadic movement, as opposed to, you might have seen it up here. I don't know if it's actually in this diagram. There's also a medial or a mesencephalic paramedian reticular formation that's involved in controlling the eyes looking up and down. We're going to focus mainly on the eyes moving side to side today. The PPRF has burst neurons and continuous neurons. This isn't too important, but basically the burst fibers are going to fire rapidly just before eye movement to try and kind of initiate that movement, whereas the continuous fibers are continuously inhibiting a process. They're continuously inhibiting, and then they stop firing just before the movement occurs. We're going to ignore continuous fibers for now. We're just going to focus solely on the burst fibers. Burst fibers, or the burst neurons, they can be inhibitory or excitatory. So if this is, we've got here, oh, come on, there we go. So left and right. In this example, we'll say that we want our eyes to turn to the left. Right, so they're following the cursor over to this direction here. This is a bird's eye view. This is our left PPRF and our right PPRF. So the left PPRF, what it's going to do is I'll try and color code this. Come on. So green means activate, right? So a left PPRF, what it's going to do is it's going to activate our left cranial nerve nuclei 4, and that's going to control our lateral rectus, right? So if we're activating that nuclei, we're going to activate our left lateral rectus. At the same time, what this is going to do, this is going to send fibers over to the cranial 3 nuclei, which then is going to innervate our medial rectus on this side. Right? So that's how we get the activation kind of part of this kind of process. However, we can't just activate muscles in order to turn. We also need to inhibit the opposing muscle, the antagonistic pair. So if we now do those in red, so the same thing, this was a excitatory burst neuron. This is an inhibitory burst neuron. So coming again from the left PPRF, we get an inhibitory burst neuron coming and innervating cranial nerve 4 nuclei, the trochlea. So that's kind of a direct effect on inhibiting that lateral rectus muscle. And in the same kind of way, it's also going to inhibit our left cranial nerve 3 nuclei, which is going to inhibit our left medial rectus. So you can see in this way that we've got activation through the left PPRF. That's going to activate the left trochlear nerve nuclei, which is going to activate the left lateral rectus, and also send a connection through to the right cranial nerve 3, the ocular motor nuclei, which is going to activate medial rectus. At the same time, we're getting inhibition of the right cranial nerve 4 nuclei, which is inhibiting the left cranial nerve 3, medial rectus, and also the right lateral rectus. And that's what's allowing that movement. It's a lot of words, I know, but once you draw it out, it does make a lot of sense. So one other thing to add in here, this is not a major point, but it will make sense in our diagram before. We call this pathway that's connecting the cranial nerve 4 to cranial nerve 3 the MLF. That is the acronym for the medial longitudinal fasciculus. Now, the MLF actually connects the nuclei of 3, 4, and 6, and so that's how they all communicate with each other in order to coordinate eye movement, and that's what's responsible for allowing this communication between 4 and 3, specifically in this kind of diagram. So if we then move back up to this diagram here, hopefully now some of these terms will make a bit more sense. So we've got the right lateral rectus nuclei, our PPRF, communicating, the right lateral rectus is communicating with the left medial rectus through the MLF. So hopefully this makes a little bit more sense now. And yeah, thanks for watching, guys. And please remember to leave any feedback that you have in the comments. I'd love to hear any comments or videos that you want me to make, anything you want me to do better. If you want me to explain anything a little bit better, answer any questions, please just let me know in the comments. Thank you.